Hello, I'm Dan Stellinga, and today I'll be telling you about our work on a 3D single fiber endoscope in the optics group in Glasgow. This is a collaboration project with David Phillips in Exeter and Thomas Sismar in Leibniz. In this project, we are trying to replace a traditional fiber bundle endoscope, where every pixel is made up of a single mode fiber approximately 10 microns in diameter, with a single multi-mode fiber endoscope, where the entire endoscope is approximately 100 microns in diameter. For comparable resolutions of about 100 pixels across, that makes our target endoscope about an order of magnitude smaller than what can be achieved with a fiber bundle endoscope. The problem with multi-mode fibers is that light passing through them is completely scrambled. In other words, it turns into something that looks a lot like a speckle pattern. However, this process is completely linear, and therefore with some clever wavefront shaping, we can turn this into a focal spot. This focal spot carries about 50% of the light passing through the fiber, with the rest spread out uniformly over the background speckle pattern. In this way, we have a fairly high signal to noise, and therefore by raster scanning this spot across a scene, we can build up a 2D image simply by collecting the backscattered light. If we then also use a pulsed source and record the time it takes for the light to return to our fiber, we can actually build up a 3D image of our scene. Our current system works at video rates in real time to give us images of objects or humans up to 3 meters away from our fiber at about 7.5 Hertz. We get both the 2D image, as can be seen in the top here, as well as the distance of each pixel from the fiber, as we can see at the bottom. We are currently working on improving all the specs of our system to more impressive numbers. However, we are already quite happy with our current results. The system is about tabletop size, but this is primarily because it was still being prototyped at the time, and we expect to be able to reduce this to a much smaller footprint in the near future. Our target markets for this are security, where we're currently in talks with the UK government, where the goal is to do covert imaging through buildings and through walls with minimal access points. Obviously, we're also looking at more traditional endoscopy targets, such as manufacturing inspection, where you want to access inside solid components with minimal access points, as well as obviously in healthcare imaging. In the latter two cases, we're looking at mainly improving the resolution of our system and its reliability when bending, whereas the first one is primarily a matter of changing the wavelength and increasing the speed of the system. Thank you for your attention.